Let's take a look at an example here. I want to determine all intervals of concavity for this function f of x equals x squared minus 1 over 2x minus 1 and identify all the inflection points. Well, obviously, the very first thing I want to do is find the first derivative. So, oops, let me change pen colors there. F prime of x equals, quotient rule, I have 2x times 2x minus 1 minus x squared minus 1 times 2 over 2x minus 1 squared. And I think I need to expand that, see if I can reduce it and get something a little bit easier to work with. See, this could be equal, what, 4x squared minus 2x minus x squared. Whoops, need to distribute that too. Minus 2x squared plus 2 all over 2x minus 1 squared. Well, this will combine to give me a 2 here, and then I can factor out a 2, and I can get 2 times x squared minus x plus 1 over 2x minus 1 squared. So there's my first derivative. Now I want to go ahead and figure out where, well, actually I don't need, I was thinking about setting this equal to 0 to look for mins and maxes, but didn't ask for that. So I'm really just looking for intervals of concavity and inflection points. So I need a second derivative. So f double x prime, the second derivative, this 2 is just going to hang around out there. So this would be, see, 2x minus 1 times 2x minus 1 squared minus x squared minus x plus 1 times 2 times 2x minus 1 times 2, just doing the chain rule there, over 2x minus 1 to the 4th. Well, I'm going to get rid of that and just make this a 4. And obviously, I need to do some simplification here. This could be 2 times. I'm going to expand this, so obviously I could put these together. No, actually, I don't think I need to expand those. So I am going to simply make this 2x minus 1. Now, they're all not going to cancel out. I was going to make them cubed to cancel out, but I'm not going to have a 2x minus 1 cubed over here to cancel it with. So I'm going to go ahead and just leave it for just a moment, just as it is. I was thinking it's going to be a shortcut there, but not really. So the most I can do here, I'm going to clean this up a little bit, minus, I'm going to distribute this 4. I get minus 4x squared minus 4x plus 4, and then a 2x minus 1 over 2x minus 1 to the 4th. See, I can cancel out one of these from each. That'll give it cubed, and that's the best I can do with that. So this is then equal to, I'll put it on here, equals 2 times, I'm going to go ahead and expand this so I can combine these and see what I end up with. This is going to be 4x squared minus 4x plus 1 minus 4x squared plus 4x minus 4. So I just distribute this negative. I dropped the parens. All over 2x minus 1 cubed. Okay, this will go away. This will go away. And this will give me a negative 3. So I end up with a negative 6 because of this 2. Negative 6 over 2x minus 1 cubed. That's my second derivative. Now, my second derivative has one value that makes this undefined. The second derivative is never 0. But it is undefined. X equals 1/2. So that's going to give me a candidate for an inflection point. So let's work with that a little bit. I'm going to have 1/2. I need to consider f double x. And just as a reminder, that second derivative, f double prime of x, is -6 over 2x minus 1 cubed. So I need a value less than 1/2. I like 0. At 0, I have a negative over negative. Again, all I care about is the sign. That's positive. I need something bigger than a half. I like 1. At 1, I have a positive in the denominator, a negative in the numerator. It's negative. Therefore, I have an inflection point at x equals 1/2. Because this is positive on this interval, the second derivative is positive, I know that it's going to be concave up. So I have our concave up on negative infinity to 1/2. And I have concave down on 1/2 to infinity. So I have addressed all the concavity and the inflection point. So a quick graph in Maple should confirm what we just did. So f of x equals x squared minus 1 over 2x minus 1. And let's go ahead and plot this. Plot f of x. X equals, all the actuals happen at 1/2, so I'm going to say like -2 to 2. Let's just do that and see what we get. And man, it just went crazy on us. So I'm going to have to put in a bounds for my y. So how about y equals -2 to 2? Let's see what happens there. And what did we see? It was concave up, and that's what we're seeing. And it's concave down. And at x equals 1/2, there's an inflection point. Now, if you also notice, if you look back at the original function, here we go, at x equals 1/2 is undefined. Actually, there's a vertical asymptote at x equals 1/2, which is exactly what we saw. This is actually a vertical asymptote. So what we did analytically matches up perfectly with our graph. Concave up, concave down. At the point where the second derivative was undefined, I see a change in concavity.